Yeah, first of all, thank you for having me. I almost said having me here at the school, but having me here at least in virtual form. I'm happy that you nevertheless organized this school, and I enjoyed it. I'm going to enjoy it also very much. Yeah, my original title was Quantum Nanophotonics, a very general one, but I decided to concentrate a little bit more in detail on some things that we are working on here. And this is the subtitle, Hybrid Integration of Quantum Emitters in Condensed Phase for Quantum Technology. A little bit lengthy title, but I hope during the course of the lecture it will become clear what I mean with this. Second remark, it's a lecture. I don't see your reaction, but if you have any question or comment, please make yourself also visible or notable. We can interrupt at any time and discuss questions. So I would be happy to do this. So please just interrupt me. Otherwise, I'm talking all the time. Maybe also I make a little break, a couple of minutes during the lecture to relax a little bit, grab a coffee, and maybe also start or motivate the discussion. Good. Let me just switch over here. Just a second. Just have to switch my pointer to order some of my, some of my slides here. Just a second. So just have to make my window panels here a little bit smaller. Okay, so now it's better. And let me give a second try here to go to the pointer again. Yes. Okay. Yeah, I would like to start with a little bit of advertisement of our place. And you see here a map of Berlin. And so there's the central building of the university in the very center of the city. And at the moment, I'm talking here from the Physics Institute, and Physics Institute is here on the southeast of Berlin, in Berlin-Adlershof, so very close to the airport here, to the new airport. Okay, this campus has some tradition, and it's a science campus, and all the science departments of Humboldt University are located here. And typically, we should have around 8,000, 9,000 students here. And so in addition to the university departments, there are about a dozen non-university research institutions and a number of smaller and very small high-tech companies. But everything, all this campus is within walking distance, and it's nicely connected to the city center. So there's quite a history. And just one remark, which I always find interesting when I'm here on the campus. It used to be an airfield in the beginning of the 20th century, and many airplanes were built here. Berlin is kind of flat and a lot of wind, so it's a good location for an airfield. And here you see an image, a photo of the famous double-deckers from the brothers Wright. And actually they built 60 or nearly 100 in their company Flugmaschine Wright GmbH in Adlershof until 1913. And then they had some administrative issues, and they decided to move back completely to the States, where they then continued building their airplanes. And you see a photo of the two of them, and maybe have a look at this building here. This is a kind of workshop building and so on. And some of these historic buildings, we still have them today. And this is an image of today, so maybe you recognize this building here. It's now a coffee shop on our campus, and so it's a site with a nice history as well. And of course, if you're there, I would like to tell you a little bit more about this. Good, I'm going to talk about quantum hybrid systems, and let me give you a child's perspective on what a hybrid system is or why you want to work with it. It's a combination of two different things. And for example, a child's perspective, you would like to give the children something healthy, but often it does not taste too well. They don't like it, like whole wheat bread and so on. And on the other hand, they prefer maybe to have something sweet, like a jelly. It tastes good, but it's not very healthy. And a hybrid system would be to combine the two things. And then hopefully you have something that combines the two advantages. So something that's healthy enough and still tastes very good. And that's the very idea of our approaches, that we try to make use of different properties of different physical systems and try to combine them to make something more useful out of it. And for quantum technology, as I will talk about, different systems have different advantages. Atoms are systems that have pure quantum properties. However, they are a little bit hard to manipulate and trap. On the other hand, semiconductor systems like quantum dots, they can rely on the established fabrication technology, but the properties are not so great. And maybe something in between are some novel emitters in the solid state. So maybe you can combine both of the properties. So the idea of the hybrid system is to exploit the advantages of two different physical systems and maybe think about some applications in quantum technology, but also it may be interesting to study joint quantum states in different physical systems. So the idea of the presentation may be three parts. I'm not so sure whether I will have enough time to talk about the third part, but first I would like to start with some fundamental effects that we are studying in these systems or with these systems. And also these fundamental effects lay the ground for applications in quantum technology. And I would like to touch upon two issues. One is quantum networks, where it goes about collecting photons, quantum light from such quantum systems. And the third part, how to combine them maybe to realize photonic quantum processors. Let me jump right in and come to the first motivation. So why using hybrid systems in quantum networks? So what is a quantum network? A quantum network consists of individual stationary quantum systems where you can store quantum information, and they're connected via quantum channels, and this is over longer distance inevitably light. They're connected by some kind of light. And in these nodes, you need to be able to store, manipulate quantum information. So very likely these different nodes consist of different physical systems. So this is very likely be some kind of huge hybrid system. And if you take a look at the very fundamental unit, the so-called Drosophila fly of maybe a quantum network, you can say the Drosophila fly of a quantum network is an atom or atom-like object connected to a photon or maybe even entangled to a photon. If you have such a system, you can try to realize other systems. For example, if you have such a system, an atom or atom-like object entangled with a photon, you can connect it with another one by just making a joint measurement on the two photons that are emitted. And in this way, you can connect different systems via measurements and create entangled states among very different physical systems. The other motivation, quantum processors. So there you want to manipulate quantum information stored in quantum states, and you would like to realize like a computer chip, maybe a chip where you have quantum systems on, and there are first approaches to build these systems in racks, and first computers are there. I'm coming back to this later during the presentation. But typically, how does, for example, a quantum photonic processor work? So a quantum computer in the future that operates with photons. So what are the major ingredients for this? You need to have some kind of sources, so light, basically, sources for quantum light. In the end, you have to detect it. You have to detect quantum light. And in the middle, you have some circuitry, so some photonic channels. And also such a system, very likely sources and detectors and the circuits will consist of different physical systems, and this is also kind of hybrid system. And here again, the Drosophila type of unit would be some atom or atom-like systems with discrete electronic or spin states, somewhat coherently coupled to a photon. And there are some first results of typical maybe photonic switches, so how to switch a photon with such an atom-like object. And this is just one paper, and you see the configuration. It's a waveguide-like structure with an atom-like object. In this case, a emitter in diamond is in the center. And you can control the state and control the flow of light in such a sample. And I will come back to this structure also later during the presentation. Yeah, a few physical effects. So what can you do with these individual quantum emitters once you have them? And I will give about 3 examples and so on about some basic effects. And in part 2, I will see how we can connect them and use them in quantum networks or later in hybrid quantum processors. This is an image here of a chain of ions. So these are real atoms, ions, and you just shine light on it and you observe the fluorescence. And here you see this prominent quantum effect of quantum jumps. So see whether I can go back here, revive the jumping. Yeah, you see that individual ions just turn on and off randomly. And this is unpredictable. Only statistically you can say when this happens. And this is a pure quantum effect, this quantum jumps. And nowadays you can realize very similar effects also with solid state emitters. So these are colloidal quantum dots. Also you just shine light on it and you observe the fluorescence, and also they turn on and off randomly. And so this is also a pure quantum effect. You can also take a look at only a single one of them. And the advantage here is at the left experiment, you need ultra-high vacuum ultra-high vacuum apparatus for this. And on the left side, it's just a sample lying on the microscope. So you can observe these effects in a much more simple experimental configuration. So this was the first advertisement for some of these atom-like emitters in the solid state. And nowadays, there's a whole zoo of these atom-like objects. So they are observed now as defects, so color defects in 2D materials. I mentioned the epitextual quantum dots, which are basically very tiny semiconductor crystals where you can trap charge carriers in. Carbon-based materials, these color defects have been observed, and maybe molecules, you can also count them as emitters in at least the condensed phase. So all of these are systems where instead of surrounding atoms by vacuum, having a very pure environment, you surround atom-like objects or molecule-like objects via a clean but non-vacuum environment, maybe by a clean crystalline environment with the wide band gap, so you can still observe the light emission from them, but they are reasonably well isolated from the interaction with the environment. Yeah, so maybe let's take a look at a first experiment that you typically do. A starting point nowadays, a standard experiment once you want to identify or investigate a single quantum emitter in maybe solid state or any kind of quantum emitter, is to prove that it basically is a single quantum emitter. And the first experiment that you do has so-called correlation measurement. So you measure the light that is emitted from such a single quantum emitter. And this configuration is typically a Hunbury-Brown twist correlator. So you make a correlation measurement on the light that is emitted from these emitters. And let's assume you have a source and you think the source should be a single atom-like object, and you expect this object can emit light. And if it's a single emitter, it can emit individual photons one by one. Sorry for this. And what is done? You send them here on a beam splitter, and you have two detectors. And these two detectors are capable of detecting individual photons, so like in a Geiger mode, so it makes click when one of these photons is detected. And what you do typically, you measure this, so you repeat this measurement very many times. So you send in light from the single photon source, you record the clicks, and you measure something like the normalized probability that these two detectors detect at the same time. And this is plotted here. So this is the time interval in between these detection events, between these two detectors. And this is so-called the normalized G2 function. It is the correlation. So how often does this happen that the two detectors detect with a time interval of 0 to a couple of 100 nanoseconds? And the clear feature that you look at is the coincidence. And you see here for this kind of source, these number of coincidences. So the coincidence counts so that the two detectors detect at the same time. This goes nearly down to 0. And this is basically accepted as a proof that you have a light emission from a single quantum object. So only one quantum is emitted at a time, and the two detectors can never click at the same time. And you can also find a very simple analytic expression for, in a sense, the probability that these two detectors click at the same time. It's just 1 minus 1 over n, where n is the number of independent quantum-like, atom-like emitters. And if it's only 1, obviously this goes down to 0, so you should never expect a coincidence count of these two detectors. Yeah, there's some debate. Well, one interpretation would be a photon is a particle-like object and it falls on a beam splitter and you cannot split it. So the photon has to decide whether it's supposed to go up or to the right. And you can never, therefore, detect it at the two detectors at the same time. So this interpretation is not quite correct, and it gives you the impression that this beam splitter, where you try to split photons, is an essential ingredient to make this, to measure this non-classical feature of the light here, so that this goes down to 0 is a purely non-classical feature. And the question that may arise is, well, is this beam splitter a fundamental part of this experiment or not? And you may say, isn't there any possibility to make a more fundamental experiment where you can prove the non-classicality of this light in a simple way? Yeah, there's indeed a way, and we did this experiment quite some time ago, and I still like it in a sense. So what's the idea? What do you need to prove that light, or at least some light, cannot be described by a classical theory? So you need, first of all, a source for quantum light. So maybe a single emitter, maybe a single defect or so in a solid state material. And the second part is a single detector and an event analyzer. So you write down the time when this detector clicks. And that's all you need. So that's all you need to prove that light from this emitter is of non-classical nature. Why is that? We did an experiment, as I mentioned, quite some time ago in two different configurations. So the light source here was an atom-like object. It was a defect center in diamond. I come back to this guy later on. And we excited it, and then we collected the fluorescence light from it. And then we sent this light from the single emitter to two different experimental setups. And this one was the standard Hunbury-Brown twist experiment. So we sent the photons to a beam splitter. Half of the light went up, half of the light went to the right, and we measured these coincidence counts. However, the other configuration was we just had a single detector here, and it's a special detector with a very short dead time, a superconducting detector. And we just recorded the clicks when these clicks happened. And also from just the number of clicks and when they happened, you can also calculate the correlation measurements. Yeah, you can calculate the probability. What's the probability that they are clicking maybe within the time interval of 0? So with both of these experimental results, you can try to make a correlation measurement. And the question would be, is there any difference in the outcome? Yeah? Or do you need this beam splitter here? And if I plot these outcomes of these two different correlation measurements in one plot, that's the next result here. So you see the red curve is measurements of this correlation with the Humboldt twist correlator. The blue one is the same correlation function correlated from a single detector only, and you see it's exactly the same. It's exactly the same curve. And so this means the simplest experiment is just a single quantum emitter and a single detector. That's all you need to prove the non-classicality of this kind of light. And the only reason for this beam splitter is that these detectors, or typical commercial detectors like silicon APDs, they have a reasonably long dead time. So you can just not in time resolve this dip here. Take a look at this. It's a couple of 10 nanoseconds. So within this time, these detectors are dead once they detect it. And for this reason, to overcome this purely technical problem, you need this beam splitter. But the interpretation that the photons are already split at the beam splitter is surely not correct. Good, nowadays, this is basically a standard. So you start with just making this measurement, and then you know, okay, I'm sure that I'm dealing with a single quantum emitter, and I'm quite sure that I'm dealing with a stream of single photons leaving the quantum emitter. Another property that you would like to change of the emitters, and we learned that they emit individual photons, is maybe it's possible to change the rate of emission. So if you put an atom in free space, it spontaneously emits light. And already this is also a quantum effect. Yeah, so there's no way you can derive a theory why an emitter in excited state, quantum mechanically it's an eigenstate, why should it spontaneously emit? And the kind of hand-waving argument for this is, yeah, vacuum is not vacuum. In the vacuum, you have vacuum fields, and they, in a sense, yeah, are pushing and motivating, in a sense, the atom or atom-like object, even in the vacuum, to emit light. It's a kind of, they kind of stimulate the emission from an excited state, even in the vacuum, because you have vacuum fields. Yeah, but this is it. The vacuum is the vacuum. Or the question is the vacuum, or can you manipulate these vacuum fields? And indeed, you can do this. And the experiment would be, well, maybe we have the vacuum and we have maybe an atom-like object depicted here as this double arrow, so a little dipole. Well, let's just put a mirror here, maybe far away, but you see, you can treat the vacuum field as if it was a real field. And you know what's happening in front of a mirror. So if you send a real electromagnetic field to a metal interface or so, it is reflected, and the boundary conditions enforce that you have a standing wave here with zero intensity next to the surface. So what happens now to the vacuum field, and what happens to the emitter? Well, now if you take a look maybe at only the vacuum field here, yeah, maybe your emitter is in a maximum of the standing wave, or it is at a minimum of the standing wave. So depending on where your atom is, and the atom is much smaller than the wavelength typically of the light that's emitted. So maybe here it does see vacuum fluctuations, here it doesn't see vacuum fluctuations. And you would expect that this alters the emission rate. And actually that's what it does. And I mentioned this first experiment to show this was from Dreckshage, 1977. So in the 70s, And they showed that indeed you can modify the spontaneous emission. So the spontaneous emission is not a natural property of an atom or an atom-like object. It's a property of the vacuum surrounding the atom-like object. And now it's very simple to do these experiments. And here I have an example which we did recently. So this is a little bit blurred, this image. You see bright spots. And these bright spots that you see here are not real atoms. They are, again, single defects, in this case in hexagonal boron nitride. So a two-dimensional 2D material. I may come back later to this. So you can just take a piece or slice of this sample, put it on a microscope, and take a look at it, and you see these individual bright spots. And maybe if you have good spatial resolution, you can just take a look at an individual bright spot here. So you have an atom-like object lying flat on your glass substrate. And you can collect the light from it. So you may be excited with a laser and you collect the fluorescence light. And now instead of moving this atom-like object up and down, we moved a metal mirror up and down. And what we used here is a very flat AFM tip, so diameter of millimeters or so. And it's a small micro manipulator, if you want to say so. So it's a small metal sphere. And we moved up and down this sphere. And we observed the fluorescence, the spontaneous emission of photons from this individual emitter here in the hexagonal boron nitride. And the results looks like this, and this really reflects the standing wave vacuum field. So this is the distance now of this tiny mirror from the defect, and you see it has this oscillatory behavior. And this solid line is just the theoretical curve, what you would expect. And it's a very nice textbook agreement. And it fades out because it's not a monochromatic field. That's the reason, yeah. So this, again, is a maybe fundamental effect, but you can also use this for something. You can use this to measure the quantum efficiency of the emitter. Why is that? The reason is because the only thing that you change here is the spontaneous radiative lifetime. And what you can measure in the experiment is the lifetime of the excited state. And the lifetime of the excited state is determined by, say, the fluorescence lifetime and also the non-radiative lifetime. And here the only thing you change is the radiative lifetime. So this visibility of this fringe tells you directly the quantum efficiency. And for this emitter, it was 30% and so on. And this gives you some knowledge of what kind of emitter you have here and how well it is coupled to the environment. So aside from this fundamental issue, it's nowadays a very useful characterization tool. Finally, the last fundamental effect is a two-photon interference. So what do you have here? It's again a property of two photons. And so this is a beam splitter, maybe a glass surface with a metal layer here to realize a 50-50 beam splitter. And in the Gedanken experiment here, you send two photons on this splitter. And classically, what could happen? Two photons can go to the left side. So this is reflected, this is transmitted. The two photons can go to the right side. So this one is transmitted, this one is reflected. Or one can be transmitted and the other one can be transmitted. Or this photon number one can be reflected and photon number two can be reflected. So now all these things can happen. And if there's no way that you can tell what of these scenarios is happening, then quantum mechanically, you do not have to sum up the probabilities, but the probability amplitudes that this is happening. And since one of these photons is reflected at an optically dense medium and the other one is reflected at an optically not so dense medium, there's a negative sign here. And it turns out that these two processes quantum mechanically destructively interfere. So for quantum mechanical object like two photons, the only thing that may happen if you send one photon in here, one photon in there, is that the two photons emit at the same side from such a beam splitter. And this process is so-called Hong-Mandel two-photon interference, and it was observed already quite some time ago by Hong and Mandel. And they created two photons in a nonlinear process. They collided these two photons on a 50-50 beam splitter and measured coincidences. And if the two photons go to one detector only, then you also expect that you never find the scenario that one photon is here and one photon is here. And this was exactly observed here in the experiment. So you never observe a coincidence. So the two photons always go to the left here or to the bottom, or the two photons go to the top. So they like to bunch together. Yeah, I come back to this also later, because this Hong-Mandel effect sorry, is a very important effect for photonic quantum computation. Good, maybe a wrap up of these fundamental effects. Yeah, you can observe this G2 function that gives you the quality of single photon states. This is a key ingredient, as I will show in the next part, for quantum key distribution. You have this Hong-Mandel dip. So this is the two-photon interference, and it happens when the two photons are identical. This is an important ingredient I did not mention. So this can be used to characterize how indistinguishable two photons are. And this is a major ingredient for photonic quantum computing, quantum repeaters. I come back to this later. And third part, this modification of the vacuum. This is also very important if you want to modify the interaction of an atom with electromagnetic fields in the environment. And also this can be used for this quantum technology applications. Good, so yeah, next part I would like to jump into maybe a first application of maybe these individual quantum emitters, and we will make use of the efficient collection of photons from these quantum emitters. So I don't know whether you would like to have some questions that we could discuss now regarding the fundamental effects. So maybe this would be a good point if you have some questions here to ask them, or some comments maybe, and then we could jump into the next part of the lecture.
Hello, can I use the microphone? Is it okay?
Yeah. Can you speak up a little bit?
I will try.
Yeah, I hear you.
I was wondering if for the detection of the quantum behavior of the light, if you have to have a photon source with a super Poissonian distribution, or it can be any. Yeah,
this is a key ingredient. So to measure this so-called anti-bunching, it's also called anti-bunching. So you need to have a non-classical light source. So like an atom, it can emit a photon. You don't know when it's happening, but what you know, if you detect one quantum of light emitted from an atom, you know for sure that your atom has to be in the ground state now. So the measurement projects your emitter to the ground state. And this means it cannot emit a photon right away. You have to bring it back to the excited state, and only then it can emit a second photon. If you have a classical light source, the detection of one photon has no effect on your light source. So at any time, you can detect another photon. And so in order to observe this non-classical feature, you have to have an atom-like object that produces this sub-Poissonian statistics, or this anti-bunched light. Yeah?
Hopefully it is clear.
Yeah.
Maybe I have a question regarding the Hong Kong Mandel effect. If it could be illustrative, if you could answer what decides actually if the photons will bunch or anti-bunch in this scenario. Because very often it's only the bunching, for example, which is shown, and you spoke about bunching, but these two scenarios should be completely identical.
In this scenario, I mentioned, and I think we have a quiz later, so I don't want to give you the answer right away. But in this scenario, I said we just sent in one photon from one side and from the left and one photon from the right. And under this initial condition, so you know you have a single photon sending in from the left and one single from the right. If these objects are bosons, like photons are, then you would have this destructive interference that I showed here, and both of the photons leave to the left or leave to the right. So maybe just as a hint, you may have a scenario where you also detect one photon's edge at each output point, but you have to use another input state for this. And maybe the last hint that I can give, you have to consider, please consider the symmetry of the states that you have. Yeah. But in this scenario, the input state, one photon coming from the left, one photon coming from the right, identical scenario for the two photons, then they are bosons and they would bunch together. If you would use electrons here, in the same situation, then the two electrons would always go to the different sides. So they are fermions, so they show a different statistical behavior. Yep. Yeah, maybe we can come back to this later.
I think this is more than enough.
Yeah, okay. But that's a very important question also.
And we have one question from Jan Čechal in the chat. So how the beam splitter experiment correlate with a classical double slit experiment? Photon passes through both slits.
This one you mean, or the one with the maybe the first one? Yeah, this is maybe a good relation because in this 100-bound twist experiment, if you send a single photon to a beam splitter, the photons are not split. Yeah, so you rather have after the beam splitter a wave function that has, in a sense, two spatial modes. So the spatial mode is one mode is going upwards, one k vector maybe is pointing upwards, and one k vector is pointing to the right. And this whole mode is occupied with one excitation, but you cannot say is the photon, or did the photon go the upper way, or did the photon go the way to the right? Only if you measure, you project to one of these possible modes. And this means in that sense, it's very similar to a double slit. You also send a single object to a double split. You don't know whether it's to the left or to the right, only if you detect it. Yeah? So that's, in principle, you can also, after the beam splitter, you can try maybe to overlap these two beams, and then it's exactly like maybe a double slit experiment. So in that sense, it's very equivalent to a double split experiment. Yeah, also a very good question.
I hope the answer was clear to Jan. Is there anyone else who wants to ask a question regarding this part of the talk?
Okay, so
doesn't seem so. So
yeah,
please continue.
Maybe we jump into the second part, and so the title is Quantum Networks, and it sounds quite spectacular, this title, but I have to maybe disappoint you a little bit. So the work that we are doing here is very trivial. We just try to collect as much light as possible from a single atom-like object. Yeah, it's as trivial as that, but that's a major ingredient to realize these kind of things. But let me start with a little bit of advertisement here. Quantum network and prominent quantum technology application is quantum key distribution, and I'm quite sure you have seen these kind of Alice, Bob, Eve configuration in different variations. So the key idea of quantum key distribution is to transfer information from Alice to Bob in a way that you can avoid that an eavesdropper is listening here. Or to be more correct, you cannot avoid that an eavesdropper is listening, but you want to make sure whether this happened or not. And here quantum key distribution comes in. And I've been using this slide for quite some time, and you can use different Alices and Bobs and Eves. And I had to exchange in the last years Bob a number of times. So this is maybe the more recent Bob that I use here. Alice is always the same in the last 16 years, but okay, this will change also soon, I guess. Good. Yeah, I don't want to go into detail here. So the key idea is basically that Alice uses individual quantum objects like photons here, And if an eavesdropper wants to gain any information, he or she has to perform a measurement on the photons. And quantum mechanically, a measurement disturbs the individual quantum systems, and this Alice and Bob can detect later as an enhanced error. So I don't want to go into detail. The only thing that I want to mention is Alice and Bob have to exchange individual photons or entangled photons and then perform measurements to see whether they have a reduced error rate. Good. Yeah, the problem here in this scenario is, well, you typically transport these quantum objects. They are photons. You can send them in optical fibers and send them through a fiber. But there's damping. Even in the fibers where the loss is low, the telecom fibers, you have damping. And typically in fiber networks, you have amplifiers, but you can't use amplifiers here. What an amplifier does, roughly speaking, it reproduces the same state. And for quantum object, this would be equivalent to see what you have, to measure it, and then to double it. And this would disturb the quantum properties already. So you cannot use, it's impossible to use a simple amplifier for this. Yeah, nevertheless, you can use the so-called quantum key distributions, but then you need the so-called trusted nodes. And this is shown here in a spectacular setup in China. So they connected Beijing and Shanghai with these QKD, but it's always subdivided in small pieces. You have an Alice and Bob here, and so you can send maybe the photons over 50 or 100 kilometers and still detect them, individual ones. But then this Bob here becomes an Alice and sends the information to the next Bob, and so on. And this means you have to trust all of these individual nodes that they don't maybe give out the information here. So it's a kind of cascade of individual atoms and Bobs. And this you want to avoid in the future. And can you avoid this? You can avoid this by generating entanglement between two distant nodes. And this is a kind of quantum amplifier, or more precisely, it's called a quantum repeater. What's the basic idea? The basic idea is, yeah, you have an atom interacting with or entangled with a photon here, an atom entangled photon state, and you have another atom entangled photon state. If you would just send over a photon over longer distance, yeah, then your loss would be maybe, something like P naught. Maybe P naught would be the probability that your photon arrives here. And this could be very small if you maybe exceed a distance of maybe 100 kilometers. And the idea would be here, well, if the atom is entangled with a photon, I can send it maybe half away. And if I do this from the other side, I can perform a joint measurement on the two photons, so-called Bell measurement. And in this way, these two photons are destroyed, but I can do a projection and then entangle these two nodes A and B. Yeah? So in this way, I created entanglement over the whole length L. However, this simple scenario doesn't help, because in order to make this work, the two photons have to arrive at the same time. And in order for this to happen, the probability is less than P naught. It's the square root of P naught. But for these two processes to happen, one photon arrives here, one photon arrives here, it's square root of P naught times square root of P naught, it's again P naught. So nothing is gained. And the key ingredient for these kind of quantum repeaters, where you try to distribute entanglement over longer distances, is you need to have some kind of memory system here. So if you have an atom entangled with a photon, then if you can send it here, if you can store it here, you can just wait until the next photon is arriving here. Yeah? And in this way, if you can wait here until this arrives and then perform the Bell measurement, you can generate entanglement here, and you gain by the square root of P. So this is in a nutshell, the concept of a quantum repeater. It requires a very efficient generation of entanglement of an atom-like object and a photon, and it requires quantum memories. And this is something that we've been working on. So there's a consortium that I just want to mention. We try to realize such a system. And the system one of the platforms that we use is the so-called solid-state defector, a solid-state defect in diamond. And I would like to say a few words about this. But again, the task is to have an atom-like object, here defect sent in diamond, entangle it with a photon, and send the photon over longer distance. Yeah, this is one of the objects, this kind of atom-like object. It's a color defect in diamond, and it's pretty well known. So this is the carbon structure of diamond, just a carbon lattice. And there are many defects in diamond. Diamond is transparent, but sometimes if you look at it, it looks a little bit bluish or pinkish or yellowish, and this comes from defects. And this defect here is just a missing carbon atom, and next to it is a nitrogen atom replacing a carbon atom, and this you can regard as kind of a molecule or atom-like object in a very clean environment. So the band gap is quite high in diamond, so light, visible light that's emitted from this defect is not interacting with the environment, so it's kind of vacuum-like situation. For this defect, the energy level structure is well known. It's basically a group of ground states, a group of excited states, and some long-lived intermediate states. And interesting enough, so this defect, you see it looks like the hyperfine states of an atom. Yeah, so we have long-lived states in the ground state, different states with a good coherence properties. And this makes this particular defect very similar to an atom. Yeah, it's very similar to an atom with a number of hyperfine ground states. If you take a look at the emission, it's a rather broad emission. This is the 300K emission of the fluorescence light. Maybe if you send just a green laser on it, and it's some reddish type of fluorescence that's coming out here. And this is the emission at low temperature. And the important emission is here at the 0 phonon line, so an emission where no phonons are involved. So this is a very clean, narrow emission, like the emission maybe from an atom where you have no interaction with the environment. Good. One of the examples that I showed in the beginning of this anti-bunching, the non-classical light source that we used for this experiment was indeed such a defect in diamond. And you can buy diamonds in bulk form or also in nano diamond form, like a grounding powder. And you can identify individual fluorescence effects. And at room temperature, make an experiment of the fluorescence from such a single defect. And this is the outcome. You know, so you see this clear anti-bunching curve, and then you know that you are dealing with a single defect. The advantage of this very defect, I mentioned this already, is that it has several ground states, like hyperfine states. And there you can play tricks that you know from atoms or ions. And one trick is to generate entanglement of the electronic states here, of the spin states, and the photon. And this is very similar to like the experiments from Alain Aspect on generating entanglement. Well, the idea is if you excite such a defect, it can emit here in two ways. It can emit a sigma plus circularly polarized photon and decay to this hyperfine state, so-called hyperfine state, or it can emit a photon and go to this hyperfine state. And if they are otherwise identical, maybe if you match this, that the frequency is identical, then the only difference between these two photons, if they would be emitted, would be the polarization. And this means after decay of such a system, you have either a sigma plus photon and the atom in this state, or you have a photon with this polarization and the atom in that state. And this means you can generate an entangled state of the photon that's emitted, polarization of the photon, and the internal state of the NV center. And this has been shown that this is possible here with the NV centers 10 years ago already. So in that sense, it's a nice solid state system where you can generate atom-like object, internal state, and photons. Yeah, now the task is, I mentioned this, well, in order to make this repeater work, you have to collect maybe all these photons with very high probability, like 90% or more than 90%. So you need to have structures that collect light from these solid state emitters. And there are different ways to do this. You can either embed them in layered structures, here different layers, and you can try to direct all of the emission in one direction. Or like for diamond, you can carve out like a lens, and then your defect would sit in the center here, and then the emission is also guided in one direction. Or this is some work we did. You can put diamond in some kind of plastic structures and try to collect a lot of light out of this. So as opposed to vacuum, diamond has a very high index of refraction. So a lot of light that's emitted from a defect inside the material would be totally internally reflected at the interfaces. And this would prevent you from collecting the photons. Okay, so one experiment that we did is here how to maybe make a device that could be a nice small and tiny part of a quantum repeater, and where you can collect a lot of photons of a defect in a diamond. And the idea here was to use a nanodiamond, so a defect in a little splinter of diamond of maybe some 10 nanometers in diameter. Try to find one where you have a single emitter in it and put it on this kind of hybrid plasmonic dielectric bullseye antenna. So I think in the next presentation, we will hear something about plasmonic effects. So I don't want to mention too much about this. So the idea is a little bit, let's assume you have a tiny diamond here with a single defect center, and it's in a layer of PMMA plastic here on silver. Then this layer acts like a waveguide. So light is emitted in this waveguide. And then you have this kind of grid structure, and this is like a grating, and constructed interference then leads to the effect that a lot of light is just emitted perpendicular to the surface here, and hopefully you can collect this with a simple lens. Good, the structures were fabricated here with from Ronan Rappapart's group in Hebrew University. You see an AFM image here, and the task was to bring a single nanoelement there. Well, typical setups, I mentioned this, for these hybrid systems and solid state emitters look like this. Many of them you can work at room temperature. So we have a sample stage. Sometimes the stage is at low temperature, maybe 4K or 10K. Then excitation light, green lasers, other lasers, and then selecting out the fluorescence from the excitation light. This is a major issue typically because, well, you only have a few photons and you have to suppress the excitation light significantly. And then you have this cameras, spectrometers, and also these coincidence units that I mentioned to prove that you indeed have quantum light. So this antenna works quite well, and it's matched to the broad emission of diamond. So the blue one is here the fluorescence of such a diamond defect center at room temperature, rather broad. And the red one is just scattered light of this type of antenna. So it matches reasonably well the fluorescence. Yeah, and this is now a picture, AFM picture of such an antenna. And at the very center of the antenna, we placed, I come back to this later, we placed a tiny diamond, maybe 20 nanometers or 30 nanometers in diameter. And due to some correlation measurements that we performed here, so you cannot resolve the dip at 0 time, but this shows this anti-bunching. So we know that basically one non-classical light emitter sits in this nano diamond, and we measured this. Before we put the diamond there, and then we try to collect the light. This is your optical image, and there you see already that it's a nice point-like emission center. So light is coming out from this individual nanodiamond sitting on this several micrometer-sized antenna. But the important information is here. This is now an angular mapping. So we have the spectrum here, and we have the angle of emission in this direction. And a lot of the emission is concentrated here at zero angle. Zero angle here means it's a perpendicular emission to the substrate. And this is basically what we want to have. We want to have this emitter in kind of flat geometry, but we want to have a lot of light, maybe all of the light coming up. Yeah, this works quite well, and yeah, you can collect up to maybe 80 or 90% of the light. And why is it so important? I mentioned this a number of times, 80 and 90%. These quantum repeaters, or even if you think about quantum networks, in the end, your emitter is a single atom or single atom-like object. What's the typical lifetime? Nanosecond, maybe. This means you have 10 to 9 photons per second. That's a reasonable number, but if you maybe plug in individual loss factors, maybe the loss through the fiber, the loss of the connectors, the loss of the photons that you cannot extract from your sample, then you easily bring this down to maybe only 1,000 photons a second. And if you think about building a communication network where you receive only 1,000 photons per second, that's not very feasible. So you want to have as many photons as possible to have a reasonable transmission rate in the end. And also, I mentioned you have to use quantum memories at some time. They have to wait until the next photon is arriving. And if your photon is coming only every couple of seconds, then you need a fantastic quantum memory that's capable of storing quantum information for seconds. And that's not really feasible. So you need to have high rates of photons. Okay, this is feasible, and here it's not so super dramatic, but at least this kind of source emits 300,000 photons per second, not too bad. And the nice thing is here you see a more compact version of this. It's a slightly other configuration, but you can see in principle you can put these nanodiamonds on some antennas, some green lenses, some integrated fiber filters, and then connect it directly to a fiber. So the whole thing you can make just a few millimeters in size. And so it's in principle a small module for quantum light emission. Good. Maybe one word connecting also to this network. So this emission is at 600 or maybe 700 nanometers. And that's not the frequency that you need if you send light through optical fibers. Optical fibers operate at the wavelength where you have the lowest loss, and the lowest loss is in the telecom band at 1.5 micrometer. So maybe that's another quiz question. So why is it at 1.5 micrometer? Or why is there a minimum? Now, there is a minimum in typical glass material. It's pretty low loss, by the way. I always tell this in the lecture. Imagine this 0.2 dB loss per kilometers. Imagine you had this loss like in the ocean or in the sea somewhere. Maybe imagine you could look down for 1 kilometer. This would be fantastic, of course. Maybe a little bit scary if you are on a boat. But so this is a fantastic low loss that you have in these fibers. Good. So one step that's missing here is some of these quantum objects, like a diamond. They emit, in a sense, at the wavelength they emit. Yeah. So, and often it's invisible, and you need it in the telecom band. So, what is needed, an additional ingredient for applications here is, yeah, maybe you have a nice system where you can produce atom-photon entanglement, like with the nitrogen vacancy center. But unfortunately, this maybe is at 700 nanometers. So you need to build in a converter that converts your single photon to a photon at 1.5 micrometer. And this has to also be done in a way that any quantum property is maintained. This can be done, fortunately, and there's just the simple standard nonlinear process that you have in some crystals can be used here. In this case, it's just a mixing of different wavelengths. So the idea is to send in light, maybe another wavelength here, does not matter so much. So maybe something more in the visible or in the near infrared. And you put it in the nonlinear crystal, and you have a nonlinear interaction of light fields. In this case, single photons, but you send in a reasonably large light field. In this case, it would be 2 micrometers or so. And then the difference frequencies results in photons that are coming out at telecom wavelength. And the nice thing of this process is it's a classical process, if you want so, this nonlinear effect. It's a classical process, but it's also a coherent process. Yeah? So you nicely maintain all the coherences in this process, so no reason to be concerned about the quantum properties not being preserved. The challenge, however, is quite obvious. Here, I gave an example for another quantum emitter at 900 nanometers, but assume you have individual photons coming in here, yeah, and you want to mix them with some light to have an efficiency of near 1, to have this non-linear process occurring. Then you need a lot of power here. So you need to mix single photons with 1 watt of power from this laser light, send it in, and then you have to subtract the photons at 1.5 micrometer from this 1 watt pump laser here. However, the wavelengths are quite different. You see 2 micrometer, 1.5, 900, or maybe 700 here. So you can do this. Yeah, so you have very nice fibers also in the telecom band, but this is a major issue, I think, to do the filtering, to getting the filtering right. Then, however, this stage of this nonlinear crystal is just something you can buy. It's a periodically poled lithium niobate crystal for the experts. You couple in light and you couple out the converted light. And this is something we did here with a number of emitters. Maybe I don't go too much in detail here. This is, for example, photons from a quantum dot, but you can also use photons from an NV center or any other photon. You just put it in there and you convert it to the infrared. Let me just jump 1 slide further. This is the last slide, just touching on this conversion. This is also another source that we used here. So we have photon pairs that you send in. One of them maybe you leave at the wavelength, the other one you convert, in this case from 900 to 1.5. The achievable efficiency is at the moment something like 30%, so it's okay, but not 90%. And then, of course, you have them at 1.5 micrometer, and the nice thing is you have hardly any loss. So in principle, you can send them over longer fiber networks. And here, just we use a coiled up fiber as a so-called quantum memory or a storage device. Yeah, it's more a delay like a storage device. But once you have the photons at 1.5 micrometer, you can send them in a fiber. It's coiled up here, circles around here, 10 kilometers, and then after some time it comes out. So in that sense, if you can, in a controlled way, send in a photon in a fiber and extract it, that's kind of a memory, or at least you can delay it for quite some long time. And then you need detectors to correlate this, and with some correlation measurement, you can do this nicely. So in principle, you have the ingredients there, efficient systems where you can have an entanglement between an internal state and photons, and you can convert it, and you can also bring it to the telecom band. And that's maybe what we want to do also in the next steps. And not only we, also others are doing this. So you try to set up nodes. In this case, it's an institute in the city center in Berlin. So in one of these buildings, you have, say, for example, these quantum emitters, and another building you have them as well. And you have a link where you try to connect these nodes. And here the links that we have are both over fibers and also over free space. And we tried some free space connectors here, and we also tried some connectors at fibers and achieved here in some demo experiments, some qubit key rates. So the rates of secret key transport is something like in the 10 kilobits per second range. That's not a world record, but these are just some first test networks that we are setting up. And maybe another view here, that's the campus in the city center of Technical University, where we have a larger cooperation with, and also here's a building, telecom building is involved as well, and we can send around these photons, and we are building up these kind of networks. And there are also other places in the world where you try to build up these networks, and we are interested in these individual nodes where you have some stationary system like maybe a diamond system or maybe an atom or a quantum dot, and everything is converted to 1.5, then you send it around, and hopefully you can create entanglement or distribute entanglement and realize this QKD. So it would be one application, but you see, I think the devil lies in the details. So you're still tackling a lot with seemingly trivial tasks, or basically classical tasks, how to collect the light and how to bring out the light, how to filter the light. So a lot of these technical issues are very important for these applications. So you know about the quantum effects, but they are there. But you need to make it in a platform, a technologically relevant platform. That's an engineering task at the moment, to be honest. I have only maybe a couple of minutes, so I cannot go into details in talking about photonic quantum processing. This would be a lecture by its own, but I would like to maybe transport the idea why hybrid systems, non-photonic hybrid systems, are also of relevance for these kind of applications as hybrid quantum processors. And yeah, let me maybe at least introduce the qubit, the photonic qubit. I talked about qubits already without explaining this. And nowadays, I hope, or I guess if you had listened to quantum mechanics lecture, so this maybe language of information science has been introduced or is used a lot nowadays. Quantum mechanics is related to information a lot, maybe not coincidentally, we don't know. But this could be a qubit. Qubit is a superposition of two states that you can separate easily. And one of the states you can call 0, and the other one you can call 1. And superposition is a coherent way of having 0 and 1 at the same time, as you say sometimes. With photons, you can realize this very easily. So you need to have an excitation, a single photon. We've seen how to generate this in two different modes. So you can easily separate two different modes in optics. And two different modes could be two polarizations. So one photon in one polarization could be state 0. One photon in the other polarization could be state 1. Or you can use spatial modes. Yeah, just use a beam splitter. Yeah, we discussed this as well. And then one photon is here. This would be 0, or one photon is there would be 1. And we had the question already. So this is actually a double slit experiment. So you perform a double slit experiment with one photon, and this would generate you a qubit. You have a superposition of the photon being here or here, being in state 0 or 1. And then the measurement is a projective measurement. So we have detectors here. You then project the states either being here or here. And of course, you can mix these states. Yeah, if you maybe have a pure state here, state 0, you can introduce another beam splitter, and this would then maybe produce a state 0 plus 1 out of the state 0. Yeah, photon being here is then with another beam splitter that you can integrate, is then transferred to a state 0 plus 1, and you can control also the crossing level here very well. And this is already a kind of so-called single qubit operation. In order to make quantum computing, you also need to be able to have a gate where two qubits interact. And this is a truth table for one of these fundamental gates. And so two qubits, one is in state 0, the other one is in state 0. And the arrow shows what this two qubit gate does. So if one qubit is in 0, the other is in 0, nothing is happening. If one is in 0, this is in 1, again, nothing is happening. One is in 1, one is in 0, again, nothing is happening. But here, if the two qubits are in state 1, then you introduce a minus sign. This is only for the pure states, and this gate should operate also if one of these qubits is in a coherent superposition. Yeah, you can easily show what the outcome would be then if you have a 0 plus 1 here and then interacting with a 1. Yeah, so it would add a minus sign only to the 1, 1 component. But if you can realize such a gate, this is enough. Yeah, this gate and single qubit operations, this would be enough to build any quantum algorithm out of it. And you see, photons don't like to interact much, but you see for this so-called control phase shift gate, something has to happen when you have here 2 of the qubits in state 1. And in the language of photons, we have already seen an idea how this could be done. So let's again assume we encode these photons in 2 spatial modes. Yeah, photon can be here, or in a superposition. And the other photon would be here, or in a superposition. And let's assume we send in maybe this mode and this mode here to a beam splitter. And then if the 2 photons are identical, quantum interference happens here. And we've seen if 1 photon is here and 1 photon is here, if it's a 50-50 beam splitter, then 2 photons would go here, 2 photons would go here. And if they come one after each other, first one, this one, and this one, then they just randomly are distributed here. So there already some kind of interaction is going on. And without going into detail, if this is not a 50-50 beam splitter, then it may happen if 1 photon is coming here, 1 photon is coming here. You have still a finite probability that 1 photon is here and 1 photon is here. But if you have this, it's a 1/3, 2/3 beam splitter, a minus sign is introduced. Right? So these 2 processes, one reflected, one transmitted, do not cancel perfectly. So you have a finite probability that 1 photon is going here and 1 photon is going here, but they would accumulate a minus sign. And if the photon is here or here, nothing is happening. So this could be an ingredient, so this Mandel effect could be an ingredient for realizing such a photonic quantum gate. And this is basically what you see in some of the first realizations of photonic quantum gates. You have sources that you send in identical photons, you have detectors, and you have some waveguides with beam splitters. And that's basically the ingredient that we need. And there are nowadays a couple of companies like Xanadu or PsiQuantum, and they are now heading for realizing these photonic quantum processors with thousands of qubits in it. For some reason, they also have very black home pages. If you take a look at this, maybe then the light looks better, I don't know. But they're taking this seriously. And the advantage of this platform would be, yeah, it's a room temperature platform in a sense. Yeah, you need to be able to generate these states. You need to have good detectors. This circuitry is just circuits that you can fabricate using integrated optics. In that sense, it's an established technology. Good. That's also something we would like to do, and I maybe would jump over a number of slides and just give you the idea of what we would like to do. So we would also like to go from realizing these photonic gates on an optical table, and we would like to replace more and more parts on an optical table with integrated elements. Yeah, going from the sources, maybe putting the sources on a chip, having the microscopic beams being on a chip and so on, and then maybe also including electrical manipulators and so on. And this is typically what you nowadays try to integrate in a photonic chip. And this could be a hybrid platform, as mentioned in the very beginning. Yeah, so we have maybe some technology for fabricating low loss, nice waveguides, but maybe your sources, if you want to put them on the chip as well, maybe they are of another material. Maybe they are semiconductors, maybe they are diamond sources, and then the detectors. Yeah, maybe you have superconducting detectors. They are again another material. So this will be clearly a hybrid integrated platform. Yeah, let me mention one activity here, as many other activities are also worldwide funded by this quantum technology efforts. Again, I just would like to depict that we're trying here to have also a circuit which includes maybe some photon sources, some modulators that we can control based on some detectors that we have here on the chip. And we also have some delay lines outside of the chip. So in that sense, it's multi-hybrid chip. So we have some sources, electronics, detectors, but maybe the delay line, it's hard to get it on chip. So we have couplers sending this to fibers and sending it back again. Yeah, one last approach that I want to introduce in the last maybe 5 minutes is how to maybe make such an integrated hybrid platform. And we already used it when I explained this experiment where we put this individual diamond piece on an antenna. And the technique that we use quite often, it's not a large-scale fabrication technique, but it works pretty nice for the first demonstrators. And this is our pick-and-place technique. It uses AFMs. And the idea is the following. So we start, in our case, one example with a glass sample with a nanodiamond here, and we put it on a glass substrate. And yeah, we select out during optical measurements one emitter that we like, and then we attach it to an AFM tip and put it on another glass substrate or another waveguide. And let me just jump forward to one slide. This will be then maybe the last slide that I will be showing. And maybe just for discussion, I have to move forward a little bit and just show you the cartoon picture. Yeah, this is one of the techniques that we can use, or that one can use for this kind of hybrid integration. So you use manipulators, AFM or micromanipulators to pick up small fragments. This could be diamond or 2D materials. And you put them in interaction with waveguides so that you have this Drosophila system, an atom-like object interacting coherently with the waveguide mode. And this is basically what, maybe if we take a look at this here, only the central image, the central emitter emits single photons, and it emits photons in the waveguide. And in this situation, we have excited the individual emitter via the waveguide. So in that sense, we can integrate also excitation sources on the chip. The sources or the excitation lasers would excite the single emitter, and the single emitter would couple photons to waveguides. In our case, it's silicon waveguide platform. So also the spin can be manipulated. So in principle, you have these different ingredients together on an integrated platform, and then you can use these effects like photon anti-bunching, Mongo-Mandel interference, detection to hopefully realize some quantum properties on these integrated chips. Good. Yeah, so this brings me already to wrap up. So just an outlook in the end, what you in principle can do with these hybrid systems. So I talked a lot about these applications in quantum technology, but maybe it's cool. I don't know, maybe you have some good ideas. If you have a bunch of atoms in a vacuum chamber, entangled with the semiconductor quantum dot on a sample on your microscope objective. So I'm sure maybe this could be also very interesting by its own if you're interested maybe in studying hybrid mesoscopic quantum systems and so forth, or applications in quantum technology. Yeah, I would like to thank you and thank our funding agencies, of course, and this part of my group. Also, many people contributed here. Without them, nothing would have happened, of course. And thank you very much for your attention. Also, we have some open positions, some advertisement. If you like to join us, just send me an email. With this, I would like to stop and thank you for your attention, and I'm happy to discuss questions. Thank you.
Thank you, Oliver. This was a wonderful talk. I see many people are already clapping. I hope you see see them. So let's go ahead to questions. I see one in the chat, so I will read it aloud.
Yeah.
From Michal Horky. How do you manipulate with nanodiamond objects? Have you tried to study how strict is the accuracy of the diamond position on antenna? What happens if we place more diamonds on antenna?
Yeah. It works pretty well. So it's an AFM technique. So we can measure the topography pretty well. And the diamonds are rather large, maybe 20 nanometers or so. So it's not an atom. And so we can pick it up, so due to surface adhesion to the AFM tip. The tricky thing is to release it then. So I'd like to stick at these tips, but once we release it, we can, if it's not in the exact position, we can then still push it around a little bit with the AFM. So the precision is maybe a couple of nanometers. And if we have unwanted diamonds, we can also push them away afterwards. So in that sense, it's quite tedious, and the students have to be very patient. So you better do this with an emitter that's stable. So you have to work with it for a couple of months, but this is doable with the diamond system, and it works pretty well.
Okay, thank you. I have a related question. How many defects is on average in this 1 nanodiamond crystal?
Yeah, here we had, in the small ones, we had maybe a little bit less than 10%. So you use irradiation to enhance the number of defects in them, and then some heating to make the nitrogen and the vacancy found each other. But for the sample we had, it was about 10%. So we first do a characterization of a lot of these nanodiamonds on a microscope. This we can do in an automated way. Then we find a good one, then we pick it up, and then we put it on the structure.
Okay, and then maybe like stupid question, but how come that you can then see the autocorrelation curve going down if you have so many defects?
Yeah. Oh, okay. We have many nanodiamonds, but we select out the defects are randomly distributed in the nanodiamonds, and in maybe 10% of them, 10% of them, we find only one defect.
So that's okay.
Many of them contain no defects at all. They don't fluoresce. And whenever we see a fluorescence blob, we take a look at this, we make a correlation measurement. And if this is, so rule of thumb, below 0.5 or so, then we pick up this very one. And then we put it there, and the defect should not be affected too much. Sometimes it's a little bit affected by this, but typically we check that it's still there. And if it's there, we know it's only a single defect.
Yeah, thank you.
It's a lot of patience is required. So it's not a large-scale fabrication technique.
Yeah. Anyone else wants to ask a question?
Yeah, if I'm allowed.
Yes, Vastik, go ahead.
So thank you for this nice talk. And what's still puzzling me is the magic behind quantum repeaters. Because if you send a classical signal over a distance, then there's a certain probability of, let's say, error. When you double the distance and the probability is low, it's basically doubled. If you put a memory inside, nothing basically happens. So what's the magic with quantum mechanics here?
Yeah, the idea is, I was a bit quick there. So first of all, you try to send over the photon to the middle node. And there you convert it again to a stationary system so that you can store it there. So then you have an entanglement between, maybe you send a Alice and the middle node, and then you wait until the next photon is transmitted successfully. So you need, of course, to have a way to check whether your other photon has arrived. And that's also not so easy. Maybe you convert it also, and then you need to be able to make sure, yeah, now it arrived, and then to perform a measurement. And then, of course, still maybe your entanglement is a little bit degraded. So what you want to do is maybe to store in the middle node more than one photon from each side, and then also perform entanglement purification. So that's a very tricky one and very challenge of this quantum repeater, that you need to be able to transfer from the flying qubit again to something that's stored, and then check also, has the other one arrived? So you need some kind of flag that goes up when the other one is there, and only then you can do the measurement. And that's highly challenging. And of course, the distance maybe is, I don't know, 300 kilometers divided by c is also quite a long time. So let's see, there's an absolute time. So this time you need to be able to store your quantum information. So you cannot say I store it for less time than that. And then also the probability is not one that your photon is sent. And so this means maybe you have to be able to store your quantum information there for at least milliseconds, maybe longer. And that's a high challenge.
Okay, thank you very much.
Then Professor Shikula wanted to ask a question.
Okay, thank you. So, hi, Oliver.
Hi.
Thank you very much for that nice talk. My question goes to quantum computers.
Yeah.
It's in principle, there are chips with integrated optics. Is there any need for further miniaturization? It means to go beyond the diffraction limit to use meta surfaces and similar stuff?
I think at the moment not. At the moment, I gave these kind of toy idea of this quantum computation. You may ask, well, it's still probabilistic, so it not works all the time. So you need to be able to make a scalable technology. And the main challenge at the moment, I think, is the photonic resources to begin with. You need to be able to generate a large number of high quality photonic quantum states, and not only single photon states. So the approaches that others are following, also the companies, they use these cluster states, so much more complicated entangled photon states. And you have to reliably fabricate them. And at the moment, I wouldn't care much if the chip is, I don't know, millimeter sized, or if it would be 10 by 10 centimeters. So this would be fine. And also you say, if you compare to superconducting computers at the moment, they are in dilution fridges. So as long as your photonic integrated platform would be as large as a dilution fridge, I wouldn't care much. However, then later on, if you want to use many of these photon states, it's much better to integrate them and also integrate the detectors. And also then you would be faster. If you maybe have to send then feedback signals over longer distances, then this gives you longer time. So in the end, you want to have short distances. But I think at the moment, the bottleneck is not the size, it's more the losses of the couplers, of the waveguides themselves, and how efficient are the detectors. So I think these, maybe whenever you go from a waveguide to another module or functional element on your chip, I think that's the major issue at the moment, to make this as low loss as possible. And then the resource states.